This is the first video in what will be quite a long series in which I will be developing a Z80 based computer system. There are dozens and dozens of simple Z80 based computer systems and kits around at the moment, and I didn't want to really just reproduce one of those. What I'm intending to design here is a system that is going to be fairly close to the sort of system that would have been developed when the Z80 was first available. So I won't be using modern large-scale SRAMs and large-scale devices. You can put a Z80 based system together in just a few hours. You can easily connect it to a ROM and some modern SRAM, and then you can connect it to PIOs, PIAs, that sort of thing, and have a system up and running very quickly. Most systems that are around will tend to use something like an RS232 interface for displaying data on a terminal. But again, I'm not going to take that route. I'm going to go down the route of designing a full system. So this will have video output direct to a CRT monitor, so not through an RS232. It will have RS232, but the actual display will be direct to a CRT monitor. I intend to use DRAM for the main RAM and just a small SRAM for the character RAM. So it will be a fairly complex system, be a fairly complex design, but hopefully will make it more interesting. All the principles for operation are fairly similar to those employed in large-scale IC designs. The difference really is this will be much more discrete in that all the inner workings of the system will hopefully be more obvious. Now, this series is really intended to promote a book I will be releasing on this project once it's complete, and that book will contain much more information than I can cram into the videos. So anyone that's interested will be able to buy the book and build their own version of this if they want to. But hopefully the videos will contain enough information to make them interesting. You'll see just how complicated this can get and how quickly it can get complicated. So the first decision I had to make was how to go about designing a system based on the Z80. So what I tend to do in cases like this is I won't start with the CPU. Now, I have put together a breadboard CPU core that I'll be using for this project, but haven't really done much design. It's just hooked up to a ROM, and it's going to be used as kind of the core test bed to test all the peripheral circuits. I won't show that in this video, we'll come back to that in a later video. So I'm going to start in what might seem a bit of an odd place for this design, but hopefully it will become clear why I'm starting with this as we go through the series. So the first thing we're going to look at is actually the video output, and as I said, I'm not going to use RS232 as the only source of data in out for this. I'm going to be creating what is a full it'll be an SRAM based character generator system, but they, if you use discrete designs like this, are quite difficult to design if you want to get a nice clear display. And in this video I'm going to go through the design as far as I've got it and explain why the various parts are required. So this is the breadboard version of the prototype, and what we've got here is we've got a character generator ROM over on the right. We've got a 2K SRAM that will hold our character information, and I will explain how all this works together later on. We've got a latch that sits between the SRAM and the ROM. We've got a shift register that takes the data from the character generator, shifts that out to the monitor, and then we've got various timers, which I'll explain the function of in a few minutes, and then some glue logic and some circuits for generating the drive signals for the monitor. So before we power this up, I'll just move it back out of the way and explain how some of these circuits work. I won't show the circuits in a lot of detail in this video, but I'll explain their general function, and then we'll see what the output is so far from this assembly. So before I start going through an explanation of the actual circuits we're using here, just a quick word on how the monitor itself works, because it's really getting your head around how the monitor works that's the key to getting a successful design for this. If it's the sort of thing you've done before, you might not find this interesting, but if you're new to this, figuring out how the monitors work is going to make life a lot easier when you come to designing these circuits. So, as with all CRT scanning monitors, we've got our display area, and it's created by a dot being scanned across the screen at a constant rate. It then quickly moves back and down a bit and then scans again, quickly moves back and down a bit and scans again. So the key to making this work is to synchronize our circuits with this scanning. And different monitors work slightly differently, but they're all really a kind of variation on a theme. The particular monitor I'm using here is one off an ADM3 terminal, but the drive boards are fairly common, and as I say, the methods for the scanning is fairly consistent for all these cheap, simple monitor types. So the way the circuits work is that when you power them up, a capacitor will start to charge, and it will start to cause the beam to scan across the screen of the CRT. What you have to do then is, on the horizontal sync input, you have to supply a sync pulse, and that sync pulse will cause the scan line to go back to the left and start again. And each time you provide the sync pulse, it will cause the line to restart. And because of the way the monitor works, it will tend to fairly consistently go all the way across, and the time period that you provide for your horizontal drive will determine how quickly it scans across. A slightly different arrangement with the vertical drive, in that there is an oscillator built into the monitor drive board that runs at a kind of fairly consistent preset value. It's about 50 Hertz or so, and that runs even if you don't give it a sync input. The horizontal won't do anything at all if you don't give it a drive, but the idea here is you provide a short sync pulse for the vertical sync at the interval you want it to synchronize, and assume you've got everything in the sort of general ballpark of what the monitor will accept. That will cause the monitor vertical retrace. So that's when the line gets to the bottom, it does a retrace, both horizontal, but in this case also vertical, to take it back to the top left hand corner, and then it will start again. This sync pulse is a fairly short duration sync pulse, and it's just to synchronize the internal oscillator of the monitor with the operation of your circuits. So the key here is the horizontal sync. So we have to generate a circuit that will time the beam moving across the screen, and then when it gets to the point where we want it to fly back, we provide our sync pulse, and that will cause the retrace to start. However, the retrace takes quite a long time, relatively speaking. In this case, for this monitor, it's about 12 microseconds, which might sound fairly quick, but bear in mind that the scan line is only about 62 microseconds, so it's quite a significant portion of the overall line time. So what we have to do with our horizontal sync is we have the portion where we're displaying data. When we get to the end of the line, we provide the start of the sync pulse, and that sync pulse has to be active for the duration of the flyback. So we end up with something like this. It's actually inverted for this monitor. This is normally high, then it goes low, and then high again. But it's the relative timing of this that's important. So We put out our video information in this portion of the horizontal sync time, and then the flyback, we don't do anything at all. In fact, what we have to do in this period is actually blank the video output, otherwise we'll get diagonal lines showing up on the screen. And then every X number of lines, we need to provide a vertical sync pulse to cause the monitor to jump back to the start of the screen. And it's choreographing this horizontal sync pulse and vertical sync pulse with our generator circuits and making sure we put data out onto the screen at the right time. So the next thing we have to do is figure out how to generate characters on the screen of the display. So it's not a vector display. We're not going to kind of draw characters by moving the beam around in this fashion. It's a raster display. So what we end up doing is, for a given character, we create it from a series of pixels. So if we break the screen into a series of imaginary areas, so I'll just do the top left hand corner of the screen here, we effectively have blocks of screen area, each one of which can be occupied by a character. And the characters are made up from a series of dots. It's very crude, of course, but hopefully you get the idea. So if we want an uppercase A, we can create it from a series of dots like this. If we want an uppercase B, we can do it in that fashion. So to generate this, what we end up doing is we create the bit pattern values in our character ROM for each of the rows in a given character. So for this top row in this character, we will look up this value required in each time we have a dot. That's a 1 in the value that's in the ROM, and where there's a space, it's a 0 value in the ROM. So for example, what I've drawn here might be something like 001000 or something like that. And then we do the same thing for the rest of the rows in the character. So in this case, we're using a 5x7 pixel character set, but it's actually in an 8x8 byte block of data. So that is in the character ROM, each consecutive block of 8 bytes represents one character. So we end up with this value, then this value, this value, this value. So we end up with a block of 8 bytes in the character ROM that, when assembled like this, will give us the character on the screen. But we don't scan each character in turn, we're scanning the entire line. So we scan the top row of the first character, we scan the top row of the next character, the top row of the next, and then we count the number of characters we want on the screen. In this case, I've selected 80. And when we get to the 80th character, we plot the top line. We then trigger the horizontal retrace. The trace goes back to the beginning, and then we start the next character line down. So it's not the next row of characters, it's the next row of pixels on the first row of characters. And then we do that, go all the way across, and we repeat that 8 times, building up each row of pixels in each character. What we then do is we move down and we do the same thing on the next row of characters down, etc., and we fill the entire screen in that manner. So the question is, where do we store the information to generate the characters, and how do we go about generating the characters? So the general principle behind doing this is fairly straightforward, but in practice it gets a bit complicated for various reasons that you'll see as we go through this. I won't be going through this entire circuit in this video. I'll give you a brief outline and we'll come back and look at it in more detail in a future video. But what makes this complicated is, firstly, you have to choreograph all this, but also you have to make sure that all your clock edges, everything is properly synchronized. Otherwise you'll get kind of jittery displays or artifacts on the display, and you won't get a nice clear display. So just to outline what we have in our design, it starts off with, of course, a clock. So in this case we are using something around 11 megahertz. That is our master clock for our video generation. That then goes into a counter that's used as it's actually a divide by 10 counter. The reason we use divide by 10, it's actually divide by 9, but it produces 10 pulses. And the reason we want to do this is because this is going to count the number of pixels in each character, but also we want to put a space between each pixel, each last pixel and first pixel for each character, so we end up with a space between the characters. Otherwise the display will look very messy. So this is effectively a divide by 9. I decided to use 74161s for this, and the reason for doing that is they're quite nice devices. They're preloadable, and of course when you come up to weird division ratios, there are various ways you can do this. You can either monitor the outputs, and when they get to a certain value you can have a gate that detects that and triggers a reset of the counter. If it's 2, 4, 8, 16, you can of course just use the output bits, because it's division by 2 for each stage. But there is an easier way with this type of device, because this would require additional gates and hence additional ICs. What you can do is, this is preloadable, so there are 4 inputs and you can preload it with a preset value. So in this case we preload it with a value of 5. And by preloading this with a value of 5, it means that when it counts from 5 upwards, when it gets to the overflow from bit 3 to bit 4 will go active. We can connect that to the load input. It will then reload 5, count back up to 15, then on 16 it will reload. So by preloading this with a value of 5, we can very easily get a divide by 9 ratio without the need for additional external components. This output then constitutes our character row clock. So that is the clock that will effectively generate or time the individual characters. The bit clock for shifting out our bits is this. So this is our bit clock, and our character clock, character row clock, is this output. The next thing we have to do is count the number of characters across the screen. So of course we have yet another counter. So in this case it's 2 4-bit counters, so it's an 8-bit counter in total, although we only use the first 7 bits of this. This is then clocked by the output of the divide by 9. We do something fairly similar with this in terms of getting it to count the number of characters we want, but we have to do something slightly different with this. Although we are using 80 characters across the screen, what we do is we count up to 80, and what we then do is preload the counter with a different value, and it carries on counting up from that point. And the reason we're doing this is we need 2 outputs from this one counter. We need one at this point, and this is when it's output a value of 80. It's actually counting from 0 to 79, and on the 80th pulse it preloads the counter with a new value, and that's so we can count up to a higher value. So we're using this counter to do 2 things. It's counting the number of characters on the screen in each row, but it's also then counting the duration of the flyback for the monitor. We need this for the blanking that we'll look at later. So that actually feeds into a flip-flop, and we use a flip-flop because we need to now synchronize everything to this. So this now becomes effectively our master clock for the entire video output process, and so we need this to clock everything to make sure that all the edges occur as and when they should do, and that they persist, the pulses persist long enough for the system to work properly. If you don't do this, you'll get a very glitchy output, and you might find certain characters are cut in half. So we now have an output that we can use as a clock that goes into our next stage counter. So far what we've done is we've counted the number of pixels in each row for each character, and now we've counted the number of characters across the screen. We now have to count the number of rows in each pixel, so that's this count. So we have, in this case, we need a divide by 10 counter. Similar sort of arrangement, and the reason we're using a divide by 10 counter is because, again, we want a blank row before each character and a blank row after each character, so we get vertical spacing of the characters on the screen. That will then count the number of rows, and this will also have another function. The lower 3 bits of this will have another function we'll come back to in a few minutes. This then feeds into yet another counter, and this is to count the number of character rows. So we've counted the number of pixel rows, and now we need to count the number of characters on the screen vertically. In this case I've selected 24, so it'll be an 80 character by 24 character display, and so we have to do something similar here and generate an output that resets when we reach 24, and it then reloads this counter and it starts again. So what we've done now is we've counted the number of pixels across each row of character, we've counted the number of characters, we've counted the number of rows in each character, including some kind of padding spacing, and we've counted the number of characters vertically on the screen. And we can now of course use this as our vertical retrace, but again we need to allow for retrace time. So now we've got all these counters sorted out, the next thing we have to do is generate our horizontal and vertical output. And they're just two outputs. I won't draw them in detail here, but there are a couple of outputs that are timed by coupling up to various outputs of these timers. The first one generates our horizontal drive, which is something that will look like that. So this is where we put the video information out, and then this portion is our retrace, and then there's another similar arrangement that again is coupled to various signals on these counters that times the correct point where we want to generate our vertical retrace. We then need to arrange some vertical blanking, and the reason for that, and I'll demonstrate this later, is if we don't blank the video during these periods, we'll get all sorts of weird things showing up on the screen. We also need to blank between the characters, so we need to blank in these areas and these areas, otherwise we'll get kind of a white matrix and weird artifact showing on the screen. And then of course we need to generate the cursor, whatever, which we'll come back to later. But this is the general principle this operates on. So now I've explained this, we'll have a look at the general layout of the circuits and see how I've gone about achieving this design and these counters. So the first counter, we've got the clock generator I'm using at the moment is just a signal generator. the clock would normally come from the CPU main clock, which is actually on the other breadboard assembly. So I'm just using a signal generator to create this, and that's fed in through this white wire. So the first counter is this one, and that's formed using a single 74LS161, and as I said, it's set to preload to a value of 5, and then on the overflow it will reload to 5 again. And that is used to create our master clock, along with a couple of other signals we use later on in the design. This feeds into a second counter, which is actually these two 74161s. This creates our character column counter, so effectively we're counting the number of character columns on the screen. And this output of this is also used to determine what the particular memory address is that's selected in the SRAM. And the reason we have to do that is because the character information to say which screen location has a particular character value, this array is stored in SRAM. So the SRAM contains information about what character to display and where. So for example, the first byte in the SRAM is this character. So if it has a value, for example, of 41 hex, then it's going to display an uppercase A, because that's what the information in the character generator ROM will cause it to do. So the output from this counter to these yellow wires is fed into the SRAM, and so as the counter progresses through the columns for the display, it generates part of the address for the SRAM, and the data coming out of that goes into a latch, and then from the latch into the character generator ROM itself. The reason we need a latch is because later on we'll need to be able to write data into the SRAM, and so it's easier if we can effectively split the display into two parts. The first part is data coming out of the counters and the SRAM to be fed into the character ROM, but if we can latch that data, then once it's been latched we can move on and do other things with the SRAM without worrying about corrupting the data going into the ROM. So the next timer, we have some various glue logic at the bottom here, which is what constitutes the flip-flops and various other glue logic required to make this work. But the output of this then feeds the next counter, and that particular counter is this one, and that, as I said, is divide by 10 counter, but the three least significant bit outputs are used to drive the three least significant bits of the ROM. And the reason we do that is because while the SRAM contains the address for the particular character that we want to select, so it will decide whether we are going to look at an A or B or C, and it will generate an address that selects a particular block of 8 bytes within the ROM. But we need a way of deciding which particular one of those 8 bytes we are going to select, and that's done based on the particular row we are trying to put onto the screen. So this timer counts from 0 up to 9, and that includes the space before and after, but the 3 bits coming out of this counter are effectively going to select the correct byte within the particular block of 8 bytes within the character ROM. So they are connected to the 3 least significant bits of the address going into the character ROM, and the values coming from the SRAM are the bits from bit 3 upwards. The output of that counter goes into yet another counter, which are these 2 devices, and they are used to select or count the row of the character. So it's counting the row on the screen from 0 to 23, so 24 characters in total. and the output from those is used as part of the address from the to go into the SRAM, because obviously we need a way of telling it not only which column we're in but also which row. So for this, for example, if we've got 80 characters across, this would be character 82, so address 82 would be the value to select the correct character for this location. So it might be an A, or B, whatever. But of course we need a way to select this, and that's what this row counter. So we have a column counter, a row counter. Those two addresses work together to select the correct byte within the SRAM. The data value there goes through the latch and feeds into the address of the ROM, and that in turn, along with the three least significant bits, is used to put data out into the shift register, and from that point it's shifted out using the bit clock and comes out as a serial data stream that is fed to the monitor. It doesn't go direct to the monitor, it has to be processed a bit first, so we'll look at that in a few minutes. So that's all the counters and timers, and these all work together. The next thing we do is we need to generate the horizontal and vertical drive, and that's what these 5 devices here are doing. They're looking at various signals and outputs of the various counters, and at the appropriate times they're generating the edges for the horizontal and vertical drive. And then finally, as I said, the video output must be processed. If we fed it direct to the monitor, because we are effectively overscanning in both directions because of the need for the retrace, we'd end up with a very weird looking display. So we have to take various signals from these counters and timers, and using the ICs on the top left and bottom left, we create a blanking signal at the appropriate times in the horizontal and vertical retrace. And the other job that these do, I've kind of built various functions into some of the circuits here. As much as possible, I've kept all these as discrete circuits to make the explanation as straightforward as possible. I'm going through this very quickly at the moment, but I will come back in the future videos and go over each of these circuits in more detail. But the secondary function I built into the blanking circuit is to give us the ability to invert the video, provide inverse video. So normally it's white on black, but by supplying an input control from the CPU, it'll be able to switch to black on white. The other thing is the cursor control. So normally the cursor control can be quite complex to generate. Now, you've probably seen already this is quite a complex thing to set up and get working, and although I'm glossing over most of the detail, getting this to all work in harmony is actually quite difficult to do. But and so because of the complexity in doing this, you'll notice if you look at the schematics for most vintage computers, as soon as they were available, designers started using CRT controller chips. It's normally a 40-pin device that does a lot of this work for you, so it has all the counters and timers and the various synchronization circuits built in. So they output the data or an address that you can feed straight into a character ROM, and they will take care of generating the horizontal, vertical sync pulses and the blanking. But I opted not to use one of those because I wanted to show this in much more detail. So with regards to the cursor generation, there are several ways you can do it. You can maintain a set of counters that work in conjunction with the counters you're using to create your display output. And what you do is when you move the cursor around the screen, you increment or decrement those counters, and then you have another circuit that compares the count of the counters here that are being used to put data onto the display with the count of your cursor position counters, and when they match, That is, when the system is outputting the character that's at the cursor position, it inverts the video and you get a black on white cursor if you want to. That obviously means using a lot more components, because you effectively have to double up the counters and timers, and also you need the comparators. Usually you'll use a magnitude comparator or something similar. And then you need the mixer circuits to mix the cursor information with the data stream coming out. I've decided to simplify that a bit for this particular design. We're using a character set that only needs the first 7 bits of the data coming from the SRAM. It's an 8-bit SRAM. So we have bit 8 spare. So I've decided to use that as the cursor position indicator for our system. So in other words, whenever a character has bit 8 or bit 7, the 8th bit set, that is where the cursor will be, and that information will of course be maintained by the Z80 CPU. And all our circuit here now needs to do is to check the output of that bit, which is this wire here, and if it's a 1, then it will cause the particular character location that's being refreshed to be inverted, so it'll be an inverse video. Very simple solution, although it does have one complication, and that is we can't just feed that direct into a mixer for the video. Otherwise we'd end up inverting the blanking information that's going to the monitor, so everything that should be blanked would show a ghost cursor. I'll demonstrate this in a few minutes. So we have to gate that information with the blanking pulse information. This all works together hopefully to give us a reasonable display output. So I'll power this up and we'll look at the display, and I'll demonstrate some various parts of what the system is doing. Okay, I'll power up the circuit. Just wait for the CRT to warm up. I'll just dim the lights, hopefully it'll cut down on the flicker. Okay, well hopefully you can see it's a very clear display. There is some flickering evident on the camera, but that's not evident in real life. That, as ever, is the frame rate of the camera. But the output of this is actually much better than it was on the original ADM3 that this monitor came from. Now, there's a lot of severe screen burn on this monitor, which is why you'll see maybe some variation in the brightness of the text. But you'll notice that it's very nice, it's linear, all the characters are very nicely presented on the screen, no artifacts, no flickering other than the frame rate flicker, properly synchronized with the monitor, so it's properly filling the display, much better than the ADM3 did that this came off. And it's showing garbage at the moment because I don't have any way as yet to write information into the SRAM, but hopefully you can see we're getting very nice clear displays. It's just the garbage that's in the SRAM when it's powered up. So the first thing I mentioned was that without the blanking we'd have some fairly odd looking displays. So if you recall, when we get to the right hand edge of the screen we start the horizontal blanking, but the counter continues counting, so it's actually continuing to output data. Kind of imagine there's an extra portion to the right of the screen, and it does that until the retrace is complete, and it does the same thing at the top as well. But if we disable the blanking, I'll just disable the blanking by moving a jumper on the board, then that's what we would get on the display. So you can see that we're getting a lot of overscan. It's possibly not that clear either, but we're now getting as well lines across the display. The retrace lines are showing up, and at the bottom you can see we're getting a lot of compression because it's displaying a lot of additional lines down here that the monitor can't actually scan to. So that's why we need the blanking on the retrace periods. Let's put this back to where it should be. So you can see that ties that up quite nicely. If I move the jumper for inverse video, this will just cause the entire screen to be inverted. Again, this has to be gated with the blanking information, otherwise you'll get effectively the entire area that we just saw being overscanned inverted, and it will show us white around the outside, which we don't want. And then finally we have the cursor information. Now at the moment I can't write into the SRAM, so it's going to display lots of cursors. So I'll just move the jumper, enable that. And just to make it a bit clearer, because most of the characters currently have that bit set, so most of the characters currently have a cursor in effect. I'm just going to invert the video so you can see a bit more clearly what the cursors will look like. So you can see now that certain characters are inverted, and normally only one of these will be inverted when we write the proper information into the SRAM. So as you can see, I've made quite a bit of progress on this particular circuit, and the reason I started with this is really because the ambiguities in trying to drive a circuit like this mean that it's easier to start with this rather than try and contrive something as a workaround once you've designed the Z80 core system. The Z80 part of it is actually the easiest part to design, but it's getting circuits like this to work reliably that is a bit trickier. Now this is almost ready to put onto a board. I can only go so far on a breadboard with this design. I can't do the entire design on breadboards all at once as I did with the transistor processor. That only ran at 1 megahertz. This is running at 11 megahertz, and trying to get a very large series of breadboards to behave themselves at that speed is very difficult, and I decided not to go that route. So what I'm doing is, as I design each section, I'm just going to turn the light back on. I'm creating small daughter boards like this. I will ultimately make a single board for the entire design, be quite a large board. But to help with the design and development, as I do each section, then I'm designing a small board like this. This is for the DRAM to make it easier, otherwise I'd end up with a huge board with lots of DRAM on it. And this will just make the entire thing more workable. So this circuit is almost ready to put onto a PCB, and I'll demonstrate that once it's done. But this does need a few additions before I can do that. Firstly, we need a multiplexer between the address lines coming from the counters and the SRAM. And the reason I need to do that is because we need to be able to write data from the CPU into that SRAM, otherwise we can't write data to the monitor. But of course we need to be able to select the appropriate address we want to write to when we're doing that. So we need to be able to disconnect these counters from the SRAM and connect the address bus of the CPU. So we need a multiplexer for that. That'll be a 12-bit multiplexer, although we're going to use 11 bits of that. And then we need a data buffer, tri-state buffer, to allow us to be able to feed data into the SRAM. And then we need a bit more glue logic. Not very much on this board, just a couple of inverters to control the output enable and the write lines of the SRAM. So that'll just be another probably 4 ICs, and I've got the design done. I just need to now get all this laid out on a PCB. So I'll get the board designed. Once that's made up, I'll demonstrate it, and then I can start explaining these circuits in far more detail. There's only so much information I can put into a video, so I will have to skip over some of it. It does get fairly involved, but for anyone that's interested, as I mentioned, I will be releasing a book that will give far more detail, along with all the schematics and the thinking behind each part of the design. But that's it for this video. In the next one we'll look at the next phase of the system design, and by the end of this series we'll hopefully have a fully functional vintage style Z80 computer system.